All right, so we're gonna start with a little bit of the PowerPoint, and then we'll move into the demo. All right, so for this sketch to weight demonstration, so I've created this big long list, which we're not going to talk through, but this is something you can kind of go reference later for, where to start and then what to even do and kind of how to do it. So I'll be stepping through this. Largely, it can be broken down into let's create a FEM, let's export it, and let's look at it and let's check it. Then let's go back and fix it. And then let's export it again and let's try and run it. And then let's check our results and see do our results make sense. And if they don't, we'll go back and fix it. All right, so I'm going to pull this here. So I have in here, so I have a series of files in this folder. And the one that we're going to be working on is this VSP model called Wing Start. And then I have a couple Python scripts in here that we'll get to that kind of work on those fixes that I talked about. And then I basically just made a .bat file to run those. And then there's a point in this process where, because of the load times on the VSP Arrow side, and also like running MyStrand, I'm gonna kind of try and do a little bit of a Julia Child cooking show thing, and put a turkey in one oven and pull a cooked turkey out of another oven. So we'll see how that works. So here's my wing. It's just a simple wing. I have a flap and I have an aileron on it. And if I go into the FEA structures tool, so it's nice to work out of this Aero Structurals tool because you can kind of bounce back and forth between the two GUIs. Sometimes I do that, sometimes I don't. But that's another little kind of trick there, is even if you're not running this top to bottom, you can kind of, make your GUI or make your structures in here, and when you're bouncing back to assembly, then you can kind of go to assembly, and then you can go back to your structure, and you can kind of do that back and forth. But for the moment, we'll just focus on the FEA structure. So I have my wing here. I'll add a structure. I'll just call it W. Now it's kind of a little bit of a habit. So the important part here, we're talking about those units. So this wing it's about a 40-foot wing. I did it in feet. But I'm going to go ahead and use feet for my VSP model. So this is in feet. And then I'm going to use the more common inches model for or unit system for the structural analysis. This way I get, stresses in PSI, and that kind of works better. And I will say that there's a fairly robust system with the materials and the properties of being able to define units appropriately, so you can kind of keep track of your units, or if you have materials in all sorts of different units, putting them in the units that they're in, and then it will convert everything to the right thing. So that's really useful. Okay, so now I have this, and I just have a skin here. But before we start meshing, I like to kind of address the material laminate properties and mesh and FEM stuff a little bit first. So one thing you'll note here, if I'm going to do like a composite wing, there are some composite lamina material properties in here. I'm working to add that agate database data in here too, so we have some more commonly used materials properties. But one thing I have created is I have sort of painstakingly put in all of the agate database into my own set of structure when I did this a while ago. And then I deleted all of the structures and all of the geoms out of that, and now I'm left with just a blank VSP sort of starter file that all it has is material properties in it, and it has material properties and a few property cards. So what I can do here is I can insert that. So I can insert the material starter, and nothing will happen because you can't see anything in this screen. But if I go here, I now have a T700 plane weave with an envelope of the hot wet and the cold dry and all the material properties. Same thing for uni, same thing for a fiberglass, and the same thing for a foam core. And then I have a couple laminate materials that I have created here already with the laminate tool. So now that kind of allows me to start with, a default list of material properties and a few commonly used for the sizes of aircraft that I'm often working on layups. So let's go ahead though, and just like for the sake of argument, let's add a laminate from this so we can kind of see. So I always forget this. We have to add the laminate as a material. So let's do like 4 core 4. We'll call it a laminate, and then all this will immediately become unchangeable. So if we go over here to 4 core 4, we can pull up the plane weave. We can, all the agate data stuff is for the plane weave is 8.6 thou. Yeah. And we'll set this to 45 degrees. And then the nice thing is it kind of keeps this. So we're going to add another one. We'll just change it to 0 degrees. Then we're going to add a core. Oops. We'll put our foam core in here. We'll say this is 0.375, or let's call it 1/4 inch core. And that's 0, but it doesn't matter because it's an isotropic material. And then we'll add a, oops, this is 4 core 4. We'll call this 3 core 2. 3 core 2. And then we'll add another 0. We got to make sure we change our thickness or we're going to have a really thick ply. That is not a valid number. And then we'll have that be 0, and then we'll add one more lamina, and we'll have that be at 45. So we got a 45, 0, 0, 45. This is really 2 core 2. So let's add that final ply. It's 45, and let's move that ply up here. So now it's 3 core 2. And that's not a symmetric laminate, but it is a laminate. So now we have 3 core 2 here, in addition to all of our other laminate material properties. All right, so one thing I like to do here first, so now we've dealt with materials, laminates. Let's go ahead and make some default property cards. So I'm just going to call this skin because we have a wing skin, and that is a shell property. And that shell property, I'm going to use that 3 core 2 down here. Let's call that there. And then let's have this be a main spar cap, and I've created a quasi iso because the bar elements don't use orthotropic material properties, they just use isotropic material properties. So I've created a sort of an iso, quasi iso T700 uni material property here. We'll keep that a rectangle. We'll call it, let's say 4 inches for the main spar cap, and we'll say 1/2 inch thick for the main spar cap. And I'm just going to do a constant cap all the way out to the tip because that way we don't have to wait for me to build up a tapered spar. And then let's do main spar web here. And we'll do the same thing. We'll say that's going to be like 8 plies at the root. And then we'll add another one. We'll call this the aft spar web. Maybe make that 6 plies. We'll add an aft spar cap. Change it to rectangle. We'll make this, let's say 2.5 inches, and we'll make it 1/4 inch. Make that 3 inches. All right, and then now I'll go ahead and add, I like to add just what I call like a flange material property. And this is, again, getting into like, do you care? For all of your ribs, they will have flanges that will add a little bit of stiffness. You can add beam elements along all the ribs to represent the flange. You can also not, and you'll get a little bit slightly more accurate answer, but you have to kind of ask yourself whether it's worth it or not. So we'll make it 1.5 inch. If you're doing this really accurately, anytime you need a rib flange where the thickness of this is the thickness of your laminate stack. So if it's 4 plies, it would be 4 times whatever. I'm just going to use 6 times the ply thickness. So that's like a 6 ply flange, just as a basic value. Now let's add a rib. Oops. Yeah. So let's add like a 4 ply rib, and then let's add like a support rib or a closeout rib, or not a closeout rib, a root rib, something that's stronger. So let's make that 8 plies. Okay, so now I kind of have a buildup of basic structure properties that I'm going to use when I make my parts. And this is useful because it's a little easy to go through and start making a bunch of stuff and then remember, oh, I need to give it properties. And so then you have to go in here, make all this, and then you have to go back in here and reassign all your stuff to everything. So this kind of speeds up the process. So what I like to do first is let's just add a spar, and let's just, oh, sorry, first let's think about our mesh. So before we do any meshing here, we always need to consider this, because if you create your part in millimeters and you have a 10,000 millimeter long wing, and then you mesh it with a max edge length of a 0.5 millimeter, then you're going to wonder why you're waiting for 45 minutes for your wing to mesh. In this case, our geometry is in feet here, but our FEA geometry is in inches. So we need this mesh to be representative of inches. So we'll start with a max of like 6 inches. And then I think I put in here what I used. Thought I did. I didn't. So we'll set the smallest one to be a 0.5 inch. We'll back up the max gap. I like to, because we don't care as much about curvature sometimes with structures, FEMs, depending on the fidelity of the FEM. So I like to back the num circle segments back to that. And then to get a little more consistent shape of a mesh, pull the growth ratio to 1.2 or 1.1 even. So
Ryan,
now
check your mid edge length there.
There we go. Thank you. Okay. All right. So now I like to save before I mesh, always, like Rob mentioned. We are going to convert these to quads because I'm running my strand. I'm going to turn off the higher order elements. So I'm only going to get quad 4s instead of quad 8s. And then let's just see if this meshes. Where did it go? It meshed. What happened? Well, what happened is you were looking at your foot geometry, and you had set your wing. In my case, I'd set my wing aft of the nose and up a little bit. So my wing was, 5 feet back and 3 feet up or something. And now it is 5 times 12 back and 3 times 12 up. So everything is moved out of your view. So the F button to refit back and forth between the two geometries is going to be really important. And I can demonstrate that. There's the wing. So we were, zoomed in here and it just disappeared. And this caught me for a while until I realized it's not a problem or anything. I think I even complained to Rob. I was like, it's not meshing at all. It's like, well, it is, just not in your viewpoint. So keep that in mind. You have to go back and forth between these a fair bit when you're doing this sort of standard approach where the VSP kind of works really well in feet or meters, and then all your aero stuff is feet per second, and that all makes sense, but you want inches when you do the FEM. Okay, so that meshed, and let's just take a look at it. Let's check the center line, make sure that we got decent mesh shape and we don't have any sort of deleted elements. So we just kind of look at that a little bit. Look at the skin a little bit. So it looks okay. Now there are some areas here. These are probably not happy elements, but for the sake of this demonstration, I'm not going to go mesh a more fine mesh or try and do like a local refinement or anything like that, because it's just going to slow down the other parts of the process later. Okay, so we have now meshed that with our polyspar. Let's call this the main spar. And now let's just start laying out our internal structure. So we've got a main spar here, and we're going to give that, we're going to keep the shell. We're going to create beam elements on that. We're going to give it the main spar web property and the main spar cap property. So we've got that. We're going to leave this at 0.25 and 0.25, just kind of the thicker part of the airfoil there. So that's sort of an efficient location for a forward spar. And then one thing I like to do is keep this up and then add a second spar, and it just pops up here and I can edit this. So we'll make that AS spar. We'll create the beam elements. This will be the aft spar, the aft cap, and then we're going to set this one to be 0.75, which is where I put the control surfaces. Okay, so now we have a main spar and an aft spar. And I won't do this a bunch, but I tend to add one or two things that are the same and then intersect and mesh, because I've done this where I've added like 12 ribs and then it blows up and I can't figure out why, and I have to go undo everything to figure out what's, what the problem is. So there, now I have two spars. You can see the beam elements represented by the lines. And then we'll go ahead and just add in the rest of the stuff. So we'll reset the part display. Look at it from the top here. I'm just going to add a bunch of ribs. This is a composite aircraft, so I'm going to kind of add ribs where I need to hook up to other things to start. So we'll add like a root rib. Let's call it rib 1. We're going to create beam elements. We're going to give it the support rib size. We'll go ahead and give it a flange, and then we'll move it to like where side of body is or something. So I'm kind of like there. Do one more notch in. Okay, so now we have a rib at the side of body. I'll leave this up. I'll add another rib. We'll just keep the numbering per what it's doing. So we'll make this a normal rib with a flange, and we'll move this to where like our inboard flap track is. Then we'll add another one for like a mid flap track, add another one for like a outboard flap track. Oops, you'll notice I forgot to change these. Rib, flange, rib, flange, and then we'll do another few for the aileron. So we'll put one, we'll try to get one right there on the end of the aileron, see if that will work. And we'll add one more for the tip. And we'll put this kind of close. Okay, so now I've got a bunch of ribs. We've got some spars. The wing isn't going to carry through on this particular design through the fuselage, but the wing spar box will. So we'll have a carry through spar box. So we're going to model that by trimming away the center there. So we'll add a trim, and we'll call this the forward trim. And we'll add the main spar, and we'll add rib 1. You see the rib 1 is the wrong direction, so we're going to try and trim inside this, and the main spar is pointed forward, so that's okay. And with trims particularly, I do them one at a time. So we'll save that. We'll intersect and mesh. All right, where to go? Hit F. There it is. Okay, so you'll notice here, it looks like I have elements here, which, wait, that might be indicative that I didn't turn off the root cap. So let's check that by using clipping, clip an X. You have to give it like 48 or something there, so we can kind of keep moving back. Okay, let's see what, sure enough, there's a rib there in the middle that I didn't want. Oops, actually, wait, let me go back a little. There it is. So there's a rib there that I didn't necessarily want, but it's put in there from the root cap. So we'll go back into our geom, go into our plan form. We'll turn the root cap to none. And then we'll come back here to structures, hit save, intersect and mesh again. All right, so now there's no root rib in the center there. And then you also can see that there's no beam elements going up and down that. All right, so that worked. I always forget turning off clipping, particularly when this inch foot thing or millimeters and meters thing, that's another way to hide yourself from your part if you don't forget to turn off clipping. So we'll add another trim. We'll call this aft trim. We'll add the aft rib and that rib 1. And this rib 1 we need to change, but the aft one is pointed the wrong way too, so we need to change it. So now we're going to trim out that back part there. Save, intersect and mesh. Okay, so now we have a spar box carry through here. Oh, the aft one isn't meshing. Sometimes this will happen where one side of the wing will mesh and one side won't. If we change this to 0.3, let's try that. Okay, now it meshed. Now that meshed. And then let's hide the wing skin. And now we have a nice internal structure, decent mesh. All this mesh is connected. So all of these, you'll see there's one node here and it's part of this element. It's part of that element. Okay. All right. So next step is to set boundary conditions. And you have to do that in the structure tool, but you can only see it in the assembly tool. So we'll do one test and then we'll go look at it in the assembly tool and see where our mesh is connected. And I'm going to kind of represent 4 connections through the shear web and the spar caps to attach this wing to the fuselage. So I'm just going to I'm going to create a BC here. I'm going to say it's only going to be on the main spar part here, and that includes the beam elements too. And I'm going to do this intentionally to capture those beam elements so that we're driving load through those instead of through the shear webs. We're going to say it's fixed in X, Y, and Z, and then we're going to give it a position here. And we're going to say Y needs to be greater than, let's say, 16 inches, and it has to be less than 20 inches. All right, so I'm going to save. I'll intersect and mesh. And Rob did bring up a good point on the questions here that there is no local refinement right now from like there is in CFD meshing. That might be something that we've added, but we haven't really kind of gotten to the point of like widespread usage of this yet. So we haven't added that feature, but it could be a feature that is worth doing, particularly for things like this, where you want it to mesh a little bit differently and not create these high aspect ratio elements. Okay, so now I'm going to go over to the assembly. I'm going to take an opportunity here to create an assembly. So I always forget to do that in that order. We're going to add our wing to it. So we have wing underscore wing. So my assembly is called wing and this is called wing. And then if we go over here to the FEM, there's a draw BCs and we can see our boundary condition. So that looks like it's about in the right place. It is grabbing those elements on the beam, so we'll transfer more load into those. We don't have a feature yet where it only grabs the element in the beam, but this will work. So I'll go through now and go back to the FEA structures, and we'll add another one on that main spar. And this one will be, I always get this wrong, so it's less than or equal to negative, or greater than or equal to negative 20, and less than or equal to negative 16. So it flips sign and it flips direction. And then we'll go ahead and add another one on another 2 on the aft spar. And we'll do the same numbers. Okay, so now we have 4 boundary conditions, intersected mesh, and we'll go look at them in the assembly. Okay, go over here to our assembly, and there you go. So we have a strip of nodes there, strip of nodes there, more nodes on the front. Okay, so we have boundary conditions, we have a mesh. Let's take an opportunity here to inspect this outside of this tool. So we'll go ahead and we'll export the assembly. Assemblies only, right? So we'll export the assembly. Notice there is a mass here, so we kind of can talk about that part. And now we will go to Pinastran, and we'll take a look at this in Pinastran. So we'll look at the BDF file. The .dat file is not really a .dat file. It's an ancillary file with groupings and definitions of groups that we haven't really worked on a lot. But the BDF file is the actual model. So we'll open up the BDF file here, which takes a few minutes. So if there are any questions, I'm now getting into this part where I'm opening and closing Pinastran a bunch, and I'm, we're gonna maybe kind of try and run VSP Arrow and stuff like that. So if you have questions, put them in the chat, and I'll try and grab them when I'm waiting for models to load. One thing I will do while this is loading is the next step that we're going to look at is some mesh quality checks. So we want to kind of, just because it meshes in VSP Arrow doesn't mean it's going to run or it's going to give you good results. So I've put into the slide deck here that will be associated with this video some just real rough ballpark mesh quality check metrics. And if you want to know more about these, I suggest looking into this reading or talking to somebody who's a structural analyst more about what are good parameters to kind of keep in. And everyone seems to have their own sort of special sauce of what they want and don't want for these. But I thought I would at least just put some things in here, and you can kind of see when we go to Pinastran now. So here's my model. I can go over here to this little browser, and I can apply. Fringe means to color the surface with that. Result displacement means to displace the model by that, and then vector is apply like a vector result as little vectors. So we'll apply the property cards to the color just to make it a little easier to read, and now you can kind of see the structure here as well. There's also, we'll use this edit geometry properties a lot. This is kind of like your browser for making things show and hide. So we'll kind of transparent, make the skin transparent a little bit. We'll scroll down here. You can look at your material orientation vectors, so you can see, make sure that your material orientation makes sense for your model. All of the, in this case, everything is fore aft on all the ribs, and it's inboard outboard for all of the skins and all the spar shear webs. We'll turn that off. We have our SPCs here. So we can show those. If later, if you connect things with 3D bar elements or rigid bar elements, that will show up here, and you can show the dependent nodes, the independent nodes, and the connections between them. And then we have our 3D bars, and those are default opaque, but we can kind of show them not opaque. So you can see the rib flanges and the spar caps, everything. Okay, so we'll pull that back to there. Go main, we'll turn it opaque. And there is an element checks in here. So you can look at these max interior angles, min interior angles, apply them to the fringe, look at the element. In this case, our min interior angle is 8.89, and we kind of were wanting greater than 10. So I'd probably want to go back in here, find where those blues are, and they're going to be on these corners here, and maybe have to drop the mesh density down an order of magnitude, or not order of magnitude, but by 50% or something, to try and get these mesh elements here to be more equilateral. Okay, so let's say we've done that, and we've created a better mesh, and we've looked at this, and we've gone through these different aspect ratio and different criteria and fixed what problems that are needed to be fixed. So the next part of this we need to talk about is load cases. So I've gone over this a couple times, but I want to kind of go through it in a little bit more detail. So we talked about that upbending, downbending, and a max wing torsion. I'm just going to show the upbending here, and a kind of an easy way to get it. So the first is, like, if you think about CL max for aircraft, they're often in the range of 1.3 to 1.6 for the vehicle level for a CL max. So you can maybe sort of use some number just roughly in there, or you can go pick CL max out and do a 2D to 3D and actually get your CL max for your aircraft, and then use that number. CL min is often more sketchy, and people don't care about it as much. So there are allowances in the FAA to either set it to negative 1.35 or negative 0.8. So you can just pick a negative 0.8 value. And then you can use the CL equation to back out based on a weight that you're looking at, which you probably have derived from like a wing area and a stall, CL max value. And then in a load factor, you can back out a speed at VA or A for that load case. And this really grabs this A corner here, which may not be a VA. VA has a bunch of requirements for it has to be greater than this and less than that, and 1% of this and that kind of thing. But for this purpose, we're just going to grab that corner there and analyze that corner. Typically, that load factor, or N1, this is load factor on the vertical axis, and this is speed on the horizontal axis. That N1 will be like 3.8 Gs or negative 1.5 Gs for general aviation aircraft, and then it reduces a little bit for transport aircraft. For UAVs are smaller, these could be much higher. And then for downbending, you just repeat this with the CL min and get a negative load factor, and that gives you a speed for those two corners. So for our wing, I did that, and I got a VA of 235 feet per second for a weight of 2,600 pounds with a CL max of 1.5. So we need to know that dynamic pressure, and we need to know it in our units in our FEA. So we convert that to dynamic pressure and then convert that to PSI, because I'm using inches for the units. And then you would further do that for a condition G or a condition E or some other downbending case, or a gust at C or F. And then you do that again for the requirements, often 2/3 of the NZ in addition to a full deflection of the roll case here, or some less than full roll deflection here and a third roll deflection here. So there's different ways to address that you have to look up in those sources that I showed in the prior talk for a roll case, but we won't be demonstrating that here. Okay, so I have a little bit about a definition for VSP aero. So now we're going to go back in here, and now I'm going to start using the aerostructural. So I'm going to show the VSP Aero GUI. Notionally, let's just start at an alpha 15. I'm going to turn off my ailerons and flaps. And then I'm going to just run this. And no geometry is defined. And this is often the case because when you go to the structures, it hides your geometry. So you have to go back here and then go back to VSP Aero. Wait for it to die. And then run it again. Now, one thing that I just did is I ran that on this wing, but I need to run that on a larger wing, and we haven't made a larger wing yet. So if I show my FEA viewer, I have this here. So I'm going to go back to this, and I'm going to copy this and paste it as a child, so it moves in with this. I'm going to call this wing inch. And then I am going to I'm going to scale this by 12. So it's big, but you notice it hasn't moved into the right place yet because I need to multiply all of my offsets by there. So now my FEA geometry is in the same position as my VLM geometry. Now, one thing that has happened here is whenever you create a copy of a structure, it duplicates that structure. It does not duplicate the materials or the properties, but it does duplicate that structure. So I'm just going to go ahead and delete this so I'm not confused. All right, so we'll go back here to our aerostructural coupled analysis. We'll show our VSP GUI. And then another thing that I like to do is go back to this wing inch and assign it to a set so that I'm always running a set. And I'm not running, whatever is shown. And that'll kind of prevent that problem earlier from happening. Okay, so we've run this. Now, if you look at your sweeps, I have a CL of 217. So this is, I'm really good at this wing design, apparently. What's happened is I'm using the 0 wing as my reference instead of the wing inch. And so all of the dimensions for references are really high. So we'll change that to wing inch. Run that again. And now we can look and we see a CFZ of like a little bit below 1.5. And one thing to note, we're always looking at the body axis for any of these load cases. So when we're trying to match us, that CL max value, there's some ways to go back and forth between CN max and CL max, but I'm just going to, for the purpose of this, assume we're trying to meet a CN max of 1.5. So we're not quite there. So I'll just bump this up by a little. And one thing to note while I'm doing this is, I have practiced this. So like this particular thing, I know I'm going to bump it up by 0.2 alpha and get 1.5. You're going to have to hunt and peck, or you're going to have to run an analysis and calculate what your actual alphas are. And then later on, when you run the structural analysis, once you've dumped pressures on this, you're going to go look at that overall Z direction load value, and it may not be right. You might have to come back here and adjust your alpha a little bit to, to basically offset or change your resulting load. So all that to say, I'm doing this in an hour. It's probably, figure 3 hours, 2 hours to do this for the first time. And then the fuselage will be quicker and easier, and the tail will be quicker and easier. You can probably put together a whole airplane in a day, if everything is kind of working and you've with the normal amount of troubleshooting. Okay, so we've run that on this. We'll launch the viewer. Just make sure we have good pressures with no weird things at the tips. And we do. We'll go back to here. So now we've kind of walking this from top to bottom. We've done the VSP Aero thing. I'm going to do W, and this is a good point here. I should probably name the assembly WA for wing assembly so that we don't get confused as to what structure we're doing. So that way we know we're doing this structure. We can show it. We've meshed it. It's good. We're going to export that mesh. So now we have our exported mesh here. And then we'll look at it in CGX. And if you have Calculix and you have it on path, then you can use this as sort of a brief way to look at this. And if you're good at Calculix, you can go through and show bad elements and do things like that. But I tend to jump to Pinastran because it has a little bit more, a little easier access to element checks and things like that. But I will use this to visualize the loads. Now, so here we've got 60 PSF, but we're not applying PSF. We're applying PSI. So we need to come back here, grab our PSI number from our load case, put in our PSI, and then we're going to try and run this. Well, I won't try and run this right now, but if we click apply loads, it'll be like 4 or 5 minutes, 6 minutes to run this. So actually, I think I will run it, and then I'm going to pull up another VSP instance, and this is where we'll jump to the sort of finished. Okay. So now, and this is a game I play, you come back here and see whether it's still circling to tell whether the loads are still being applied. And this should take about six minutes to apply, I think. Okay, so now we're back over here, and I'm going to do a little bit of logistics work here. So in my demo, we have this wing start Nastran BDF file WA for the wing analysis. And this is the file that is the model. So we pull it up here, you'll see that case control deck and that executive control deck. And then we have this is sort of the inverse of what will happen once you run this through Pinastran, but we have the properties at the top, and the materials at the top, and the SPCs at the top. And then it starts moving into grid, which is node definition and element definition. And that's the bulk of the data. And that's pretty much all this is. Pinastran will flip all the stuff that's not grid or element to the bottom, which is kind of convention. But I don't know, I like being able to see all the things I care about at the top. And you may have to hand edit this if you're doing, your own loads and you're not pulling loads from VSP Arrow, or you're not using Pinastran, the Python tool or library to create your own loads. You'll come in here and you'll start adding force cards, at this and at this level. So there's also this Calculix file, and what's happening right now is this apply loads is creating a Calculix underscore static and a Calculix underscore buckle. And I have written a little Python script, which I will share with everyone here, that pulls in, gives us a load set ID, because you need to sort of identify the load set. And that is important because the executive case here, the default set is a load set of 1. So I have it set, you can apply, whatever load set number to this VSP Arrow run that you want, but you'll need to go in and do a little bit of hand editing. If you want to do multiple ones, you can add all those resulting P-load pressures down at the bottom here, but then you'll need to copy this subcase and paste it, make another subcase 2 and have it load 2. And you can kind of build up your, a run with a bunch of different load cases there. It takes in the Calculix file, an input file, a Nastran input file, and a Nastran output file name. And then basically this just transfers all of the loads from one to the other. There's also a fix that I'm running here, and this fix goes through and loops through all the model materials and takes the G12, which is the shear in plane, and applies that same value to the G1Z and G2Z, which are the out of plane shear moduli. So that's an important part, like we talked about before. So we'll run that as well. Okay, let's see how we're doing, see whether I need to jump or if we're good. So here, still working. Okay, so what I'm going to do is I'm going to switch over to this files folder. I'm going to grab my tools here. I'm going to come over here. So this is what will come out of this. So we'll have a calculus WA calculus.static.input file. And then we'll have a nastran .bdf file. And I actually realized that I didn't copy over the, I'm remeshing it so this won't be consistent. So we'll have a nastran. This will be the file that we already have in the other demo. So let me check out this one last time. Just open this quickly. Grab all these payloads. Leave those out. Okay. So we'll say that this is what we are working with now. So this, we have our nastran.bdf file. Delete. All of this stuff here. And we have our calculus.static file. And if we look at the .bat here, I'm going to pull in the wing start calculus.static file. I'm going to pull in the wing start wing assembly nastran file, and I'm going to output this nastran static file. Then I'm going to take that static file and I'm going to run it through my fixes, and I'm going to come up with a static fixed file. So if we go to open a terminal here, let's see if this works. Okay. All right, so we've run those two scripts, and now we have a nastran static and a nastran static fixed. So now we can go here into PyNastran and we can load up the one we're going to run, nastran static fixed here. We'll take a few minutes to open this. Okay, so now if you open up geometry here, you'll see there's a load case with pressures, and we can apply those pressures to the fringe, and now we can see we've got our pressures applied to the surface. And one thing that's of note here, if you've done more of this, this is I'm using VSP Aero in the VLM mode. I'm doing that because you can then apply representative pressures from control deflections, flaps, and ailerons, and things like that. And in order to capture, if you really wanted to do this for a wing and capture that, completely, you would want to break out the flap and break out the aileron. And if you're trying to do this with the VSP Aero pressure mapping, you would need to model those as separate components, attach them to the wing, which you can do. And I have done that before. In fact, we can look at that here. So you can see here there's a flap and there's an aileron, and then there's connections between this to the main spar for the wing. So you can model all of this, and then you'll get pressures applied to the flap, pressures applied to the main wing, and you can have the full lift. It's important to note, if you're just doing a wing and you've you have a non-structural leading edge, you cut that off, and you're just looking at the wing box and you just want to load that up, and you cut the trailing edge off, and then you apply your pressures, you're going to miss 30 or 40% of the load, because a lot of it's getting applied up here, and then some of it's getting applied back here. So if that's what you're trying to do, you probably need to take your loads, drive them down to discrete loads that you can apply at sections along the wing instead of this pressure mapping. The other thing is the distribution will look a little different, because it's taking that flat plate VLM, or that camber surface VLM, and applying half of it to the top and half of it to the bottom. It tends to focus more of the pressures on the leading edge than if you run panel code. It'll look a little more sort of normal. But the key thing here is you have a pressure distribution. You can run your loads, run your analysis. You can look at your results, see if your pitching moment at your SPCs, at your reaction points, makes sense, and that your vertical shear makes sense. Compare those back to your loads, and then you might have to iterate on that, but at least you can understand that what you put in, you get out, and then you start and then manipulate it to get out what you're intending to get out, which would be 3.8 Gs of your vehicle weight. Okay, so we have that. So now we have pressures, we have boundary conditions, we have a good mesh, or good, this isn't a good mesh, but you would have worked on this to make it a better mesh. So now it's about running PyNest, or running MyStrand. So if we come back here to this folder, and this is where I'm going to cheat a little bit, and I'm going to run the MyStrand 16, which you need to compile from source yourself, because it works with this model. But again, if you wait for the new shells, you'll get a much better shell element, and then that will probably be where things really start gelling between these. So I will run MyStrand 16. And I will go back here, go to our demo, go to our files folder here, and we'll just grab our name. Let's see if it works. All right, so now MyStrand is creating all sorts of files. It's running the analysis. It'll take 5 or so minutes to run this analysis, and you should have results that we can look at. So we'll now jump to those results. Again, this is a little cooking show like, rather than waiting for this to keep running. So we'll go here. We'll go back to this. We'll open up our already kind of pre-solved model. And I'm reopening the model just because it was a different mesh. I used a spar instead of a poly spar on this old one. It's a little, hokier than what we're running right now, but this way we don't have to wait for the MyStrand run. Okay, so here, same thing, similar model, similar pressures. And then we'll open this to open the results file. The results file, there's 2 results files. There's OP2, and then there is the FO6. And one of the first things we'll do is we'll open this and just see, did we even get anything that was remotely sensible here? So we go in here, displacement, we'll apply that to displacement. And look, we have a wing that's bending up, which is the direction we expected to bend up. I'm not sure why there we go. It's bending up 12 inches, which is not an unreasonable displacement for, particularly because this spar caps are pretty thick all the way out here. And so we have a result there, and we can go, forward, and we can plot our plate strains, or max principal plate strains, and we can see the strains on the plates. And then we can go into the forces, our bar forces, and we can plot our axial force, and it'll show. It's a little hard to see here with the 3D bars on, so we can turn off the 3D bars. And then you can kind of see the stress results. So we have a high tension stress in our bar, in our caps, and high compression stress in our caps. So that all kind of makes sense. So we're getting somewhat sensible results. The next step in this is to go back here and look at our FO6 file. And this is a big file that echoes, if you put an echo, it echoes the entire model. And then it also outputs sort of numerical results. And you can do this through a post processor as well. But if we type in SPC forces, we will get a summation of all of our SPC forces. So all of our SPCs was our boundary conditions. These are all the nodes that are comprise those boundary conditions. These are all the forces on those individual nodes. And then if we sum all that up, we get a Z value, a reaction force of 1, 2, 3, 4. So 1,200 pounds. And the reaction force is down. So that's less than 2,600 pounds. So we need to, figure out what's going on there and apply our loads differently. Oh, wait, no, 12,000. 1, 2, 3, 4. Yeah, sorry, 12,000 pounds. So if we were to do calculator and we were to do 2,600 pounds times 3.8 Gs, that's 9,800 pounds. So we're in the ballpark. It's not the right number. It's definitely off, but that's how you would sort of go back to your source and say, okay, am I getting what I'm expecting? Am I actually stressing the structure under the appropriate load? And that would be the kind of checks that I would do. Then we would go, whoops, where'd my Nastran go? There it is. So then you would start looking at your strains and stresses, comparing them to allowables, going back to VSP here, and changing your, maybe changing your cap properties, change this to, 0.75 inches, or put in a tapered spar, or, start messing with your structure until you get positive margins or positive margins against all of your requirements. You might have displacement requirements. You might want to thicken things up so that the wing doesn't displace as much. You can run modal analyses and stiffen things up due to, to modes being at prop blade pass frequencies or things like that. So that's kind of the nutshell, in a nutshell, sort of a start to end. And the result of all of this would be you would be coming back to here. You'll be looking at your let me go here to this. So I talk a little bit in here about the things that we talked about. I won't go over this, but when we're talking about sizing the structure, this is really where you need some experience to do this, or you need to go work with somebody who can kind of teach you through particularly at the conceptual level, the sort of rules of thumb and the quicker ways of doing this and not get buried under 25 different failure criteria and trying to size particularly composite structure. So these are some, options you can use. 3K to 6K microstrain as a sort of a starting place for ultimate strains. Don't forget that you've run a limit load condition, because we did the 4 Gs, 3.8 Gs. Here, this is limit load. You need to multiply that by 1.5 or whatever safety factor you're using to get to ultimate load. And then, you may need to rerun a buckling analysis once that's a function in MyStran, or if you're running Nastran, run a buckling analysis and change the acreage of skins, the thicknesses or the core thickness, things like that, to do analytical buckling. You might need to do hand calcs for crippling to size the structure. So this is the part where it gets a little messy, but if you're working with somebody like myself or other structural analysts, you can kind of get this part working. Okay, So then when we're at the last part, which is the, what we really want to be doing here, which is, I guess I just have everything I need here. When you export that assembly mesh, it gives you a mass, which is 0.13 pounds. So I've got CL of 217 and 0.13 pounds of mass. So I think I've done some pretty sweet aircraft design work here. But keep in mind that you're using the FEA units that you set. In this case, that's pounds force second squared per inch for mass. So I need to convert that to pounds force in, to weight in pounds force. So I need to multiply that by, this gravity in terms of inches per second squared. So I do that and I get a structural weight of 51.2 pounds. Now this is a structural weight of just the items you have in there. So it includes the flanges of the ribs, but it doesn't include any hard points. It doesn't include any attachments for ailerons or controls or fuel, things like that. Fuel would probably not be in your structural mass fraction. It also doesn't include any bonds or any fasteners, so you need to make some estimates for that. You could add all those masses to this, divide by your overall max takeoff weight, and now you have a mass fraction, structural mass fraction for the wing. Go do that for the fuselage, the empennage, and you now have your mass fraction, structural mass fraction estimate that you can use for your conceptual design. And then that feeds back into your max takeoff weight, which feeds back into your wing size, which feeds back into your structural analysis. So let's say we needed to make the wing 5 feet longer. So you would just go back to VSP here. You would make your wing a little bigger. Can't see it because it's down here. Make your wing a little bigger. You'd have to re-export this. But if you go back to your wing structure and rerun it, there, now you have your bigger wing with all of the ribs in the same places and everything else. So then you would just run through this iteration with a larger size structure. And that's the point where things tend to slow down, I think, with traditional structural analysis, is you do all this work in CAD to make this wing bigger, then you hand it off to an analyst. The analyst recreates a whole FEM from scratch or modifies a FEM to make it work. And then runs through that loop as well. So this is really where the conceptual VSP Aero connection or VSP, part of having the structures tool coupled with an arrow tool, coupled with a design tool all in one is really helpful. All right, so that's kind of the end of that talk. If anybody has any questions about that, please type them while I'm pulling up the next slideshow.